We're going to continue working with average rates of change. If you notice, we've still been talking about slopes or average rates of change. Last time it was with linear and quadratic functions. Today we're going to extend it to all types of polynomial functions. Now, what's a polynomial, you might ask? That's a great question. Textbook definition is as follows. A polynomial function is any function representation equivalent to the analytical form, and I'm not going to read all of that to you because you're not going to listen. N is a positive integer, meaning this value here is a positive integer, and AI is a real number for each I from 1 to n. That is a really mathematical way of saying that all of these coefficients are real numbers, not complex, not imaginary numbers. And then also that a sub n is non-zero, meaning the first term can't be 0, because then otherwise it's a constant function. Okay. Now, some vocabulary you would have learned in Algebra 2, just to review. It says in example 1, find the leading coefficient. What is a leading coefficient? Do we remember that one from Algebra 2? The first one. Okay, it's the first one when written in standard form, but really your leading coefficient is a sub n, meaning it is the very first coefficient when written in standard form, or the coefficient of the leading term. The leading term is the term a sub n times x to the n power, your biggest power. So the term with the biggest power, the leading coefficient, is in front of it. Does anyone remember what a degree is? The largest exponent is the degree. Typically, it's the first exponent, but it might not be written in standard form, so we just have to make sure we actually look through the whole thing to find the largest exponent. So if we are trying to find the leading coefficient and the degree for these polynomial functions, we really just need to look at that leading term. So in this first one, what is the leading term? 3x to the 4th. So my leading coefficient is 3, and my degree is 4. Does anyone remember the specific name for a 4th degree function? Quartic. That was a little bonus. It's a quartic function. Okay, cool. Now what about b? Is the leading coefficient 12? It is not, because if you notice, the leading term, meaning the largest exponent, is just not written in front because they didn't write this in standard form. So what is my leading coefficient here? And what's my degree? What is that called when it's degree 3? Do we remember? Cubic. Very good, because it's something to the 3rd power is cubed, so the function is called cubic. Okay, how about this third one, c? What is the leading term? Well, there's only one term, so here we go. Meaning, what is the leading coefficient? 4. And what's the degree? Not quite. Thank you for falling for my trick. If we have x to the 1st power, isn't that the same thing as x? Do you see an x in this formula? What happens when you take x to the 0 power? What does that equal to? 1. This is like 4 times x to the 0 power, since the x term is gone. So what's the actual degree here? 0. So your constant functions technically have a degree 0. That's not something you would have seen before, probably. Does that feel okay, talking about leading coefficients and all that? Okay. Another something you've probably talked about before, but not with this vocabulary, is extrema. So your extrema of a polynomial, of a graph, are the minimums and maximums of the functions. We call them extrema because they are the extreme values. Extreme high, extreme low, maximum, minimum. So we call them extrema. There are 2 types of extrema. You can have your relative or local extrema, and then you have your absolute or global extrema. Absolute kind of makes sense why it's called that, because it is the absolutely biggest or smallest. Relative or local just that means that the polynomial switches between decreasing and increasing, or it's at an endpoint if the polynomial has a restricted domain. Okay, that's a lot of words. Let me tell you what all that means. If we switch the polynomial from decreasing to increasing, What kind of extrema is that? Is that a maximum or a minimum? Is it a little point or a tall point? This is a minimum. If you switch the graph from increasing to decreasing, what kind is that? Maximum. That's what I'm talking about when the graph changes from decreasing to increasing or increasing to decreasing. So every time it switches back and forth, you will have a relative maximum or a local maximum, because compared to the stuff around it, it's really big or really small. Also at endpoints, you will have extrema. So if I looked at this graph right here, I see that I have an endpoint on the left. I have a hill, I have a valley, I have a hill. Do I have an endpoint on the right side? No, it's kind of hard to tell because it didn't print great, but that is an arrow, which means we are not restricted on the domain on that side. There's no boundary on that side. There's only a boundary on the left side. So if we needed to identify our relative or our local extrema here, what two x values I should say, are their local minimums or small points? This would be one of them because it's low at an endpoint. What's the x value? -4, so we know that's one of our local minimums. What's the other one? 0, because here is another low point at x value of 0. What are my, What are my local maximums? -2 and 3, because those are the x values where they occur. I have a maximum at -2 because that's a hill. I have a maximum at 3 because that's a hill. Now these again are local maxes and mins. A different word we're going to be using is an absolute extrema, absolute max and absolute min. When we're talking about the absolute or the global, we're talking about the biggest of all maximums or the smallest of all minimums are called the absolute versions of those. Not all graphs have global maxes and mins. This one doesn't even have both of them. Because if we look, we had all of these points. I'm going to highlight them again just so you can see. But we didn't have a point on this side, which means what's happening on this side of the graph? It's going to keep going downwards, correct? Okay, so is this graph going to have an absolute maximum or an absolute minimum? It doesn't have both. Maximum, because this arrow says I'm going to keep going down and down and down. So is this actually the lowest it goes? No. So this has an absolute maximum at the value 2, or at the height 2, at the x value 3. Meaning at the x value 3, the highest it goes is 2. And we just said that there was no absolute minimum. So we're just going to say not available or none. Now, if this were an actual endpoint instead of an arrow, this would have a minimum here because that's the lowest it goes if it was bounded on both sides. But this is going to keep going off screen, so it's not the lowest. Does that vocabulary make sense? Local versus absolute? Local is any hill or valley or endpoint. Absolute is the highest hill or the lowest valley. Okay, yes ma'am. That's a great question. When it says absolute maximum, it's wanting to know how high does it actually go. The highest it goes is 2. And that occurs at the x value of 3. So the highest it goes is 2. At what location? 3. Can we try some practice problems with just identifying extrema? Okay, example 2. Find and classify each type of extrema for the functions below or write not available if it's not there. Okay, let's look at our graph for a second. Do we have endpoints? No, these are both arrows. We've got to look close. I know that's a little bit of a small graph for you, but those are arrows, so we'll emphasize. Okay, but what does it have? Has a maximum here. So that is a relative maximum at 1. And we're saying it does not have any relative minimum because it never curves and makes a valley. So it definitely doesn't have any absolute minimum. If it doesn't even have a relative one, it can't have an absolute. Does it have an absolute maximum? How high does it go? 3. And where does that occur? At 1. So yes, your relative extrema can also then be classified as an absolute. You will only have one absolute, but you can have multiple local. Yes? Let's see if we understand. At the back, there are 2 examples up here at the top. Try them real fast. We'll see if we have to edit a little bit, but that's okay. Give these a little shot. Okay, first thing I do when I do these kinds of problems is I make sure I know what's happening on the graph. So I notice that there is an endpoint here. We have a little valley, we have a hill, and then on this side I have an arrow. I have to make sure I clock all of those things so that I can answer the questions appropriately. Okay, relative minimums is talking about all of the valleys. At what x value does the only valley here occur? -2. Maximums happen at, or relative maximums happened at, oh my gosh, hills or at endpoints potentially. There are 2 relative maximums here. The endpoint -4 and then the hill at 3 are both of our relative maximums. Does this graph have an absolute minimum? No, why not? Because the arrow going down is going to keep it going down, so you'll never reach a lowest point. It'd be negative infinity. But it does have an absolute maximum. How high does it go? At what value? 3. Again, that's because this point right here is still our absolute maximum. That's the highest the graph is going to go since no arrows go higher than that. For part C, relative minimum, same questions. Okay, so I'm going to look at the graph again. I notice this time I have endpoint, valley, hill, valley, endpoint. So all of those are going to be pieces of extrema for me. I just have to classify them. There should be 2 minimums. Where do those 2 minimums occur? -3 and 3. Those are both relative minimums because they're both valleys. There are 3 relative maximums. What are they? -4, 0, and 5. All of those are highest points locally compared to the stuff around it. This one also has both an absolute minimum and an absolute maximum. So we want to know the highest it goes and the lowest it goes. So I notice that this is the lowest point that it goes. How low does it go? At what x value? -3. And then I notice that this is the highest that it goes. How high does it go? 4 at what x value? 5. So your answers for absolute max and min should always also be on the list for relative maxes and mins. Because they're all relative and only one of them potentially could be the absolutes. Does that make sense? Okay. Moving on a little bit. Some fun facts about polynomials. These are just nice things to know. And I'll explain why they work because they make a lot of sense once you think about them. Between any 2 real zeros of a polynomial, there must be at least one local minimum or local maximum. Now let's talk about what that means. If I were graphing some function and I had 2 real zeros, what's a 0 again? Where it goes through the x-axis. So here's my x-axis and I have 2 zeros. If I were playing connect the dots and I know that it's a polynomial, which means that it's continuous, we could have a graph that looks like this. But I know that it has to touch both of those things, right? What has it created in the center? In between those 2 points? A minimum. Now let's say that it didn't look like that and that instead between these 2 points on my x-axis it went up like this. I still have to go back and touch that axis, so what has it created on the top? So between any 2 zeros, there is at least one turning point because it has to go through the x-axis, turn around, and come back down through the x-axis. So there is at least one local max or local min. Another fun fact for you today, polynomials of even degree, which means 2, 4, 6, 8, must have either a global maximum or a global minimum. Odd functions, not so much. Your even functions must. Now, why? What do we know about even functions from Algebra 2? Maybe something to do with some words called end behavior. Do we remember those words? End behavior is basically the direction that the arrows are going when you stop graphing on a piece of paper. So if I have an even function, the most basic even function is a quadratic. Here's my super basic quadratic. It's even because the arrows go the same direction, either both up or both down. If they go both up, there has to be a lowest point because neither of these arrows is going down. So they both go up, that means there has to be a lowest point, a global minimum. Even if I make a sad parabola, so both arrows are going downwards, it has created a global max. Now this works for any degree that is even, because if you have a quartic function, it looks like a W, there's still a lowest point. Or a negative quartic, it looks like an M, there's still a highest point. And that'll keep going for any degree evenly, because even end behavior is that the arrows go the same direction, either both up or both down. And if they're going the same direction, then there has to be a global max or global min in between them. So if you're thinking to yourself, oh dear, end behavior, I trashed that out of my brain. I need you to go try to find it in your brain somewhere, because you learned and talked about it all last year, so you need it back again. Or 2 years ago if it's been a minute since you took Algebra 2. All right, new vocabulary for us today. I've been mentioning this kind of as we've gone. Here's the first time we're going to define it. It's called a point of inflection. I'm going to use the shorthand POI. Is that okay with everybody? Point of inflection. It's point of interest when you go to maps, like whenever you Google stuff, they're called point of interest. But point of inflection for us. A point of inflection is going to occur when the function changes from concave up to down or from concave down to up. At a point of inflection, the rate of change of a function changes from increasing to decreasing or from decreasing to increasing. So again, if we think about concave up, if I have a graph that's concave up and then all of a sudden it switches to concave down, there's a point where it has to change between them. We've identified these before, you just didn't know what they were called. This is when it switches from concave up to concave down or concave down to concave up. Applying that to rate of change, that means that the rate of change changes from increasing, concave up, to decreasing, concave down. So we're going to use this graph here, and I'm going to struggle to show everything all at once. Okay. It says, the graph of g of x is shown on the figure. Use the graph of g to answer the following. Find any values of g where g has, find any values of x where g has a point of inflection. Before we do that, take your highlighter, and I want you to highlight all of the extrema, maxes and mins. So if I were going to highlight just extrema, which is maxes and mins, I'd have one here, here, and here. Do you agree? Yes. It's very tempting to call extrema points of inflection. Those are different things. So in the answers you give me, you cannot answer the 3 dots we just made red or whatever you colored it for highlighter. Those are extrema, not points of inflection. In fact, let's just write down what they are. This is a minimum, this is a minimum, this is a maximum. That way we're not tempted to include them as points of inflection. But if we also looked at this graph for where it was concave up versus concave down, okay, let's remember those words. Concave up means it looks like a little bowl that's going up. So this section right here, would you agree it looks like it's concave up? And then what happens? Turns into concave down until about here. And then it switches back again to concave up. Those places where I switched colors, those are the points of inflection. So they don't occur at extrema pieces. They occur here and here, where we would change our color coding from concave up to concave down or vice versa. So to actually answer the question, it says, find the values of x where g has a point of inflection. Where are the two x values where I switched colors? X equal to -1 and 1. Those are my points of inflection. At those 2 points on my graph, those two x values, I switched from having an upward facing bowl to a downward facing bowl. That's what we're talking about with points of inflection. If we were to find the point of inflection for just this section right here, at what point does it change from concave up to concave down? Ish. About -2. Do you see that this is a concave up bowl and this is a concave down? So this is the point of inflection, different than the extrema. In between the extrema, but different than them. So now that we know where we change from concave up to concave down, again, it's going to help me describe these graphs more eloquently as we continue to add vocabulary to our explanations. Now, if you've noticed, I've started to give you a lot of blanks and a lot of sentence stems. Eventually, those are going to go away. So I need us to also clock what we're writing each time, because you will have to eventually write the full sentences out, but for now we're just filling in a blank because it's the third week of school. We want to see on the interval from 3 to 4 if the rate of change of g is increasing or decreasing. So if we look at our graph from 3 to 4, is it concave up or concave down? Up. When it's concave up, what's happening to my rate of change? It's increasing. So my rate of change is increasing because the graph is concave up on that interval. What about from -4 to -3? Ooh, I've heard both now. Is it concave up or is it concave down? It is concave up. We're looking here from -4 to -3. That's concave up. I know it looks like it's going down, but technically it is increasing because it's technically negative, and as negatives flatten out, they're increasing because you're getting less negative, which means you're increasing. How about from -1 to 1? That one is decreasing now. Why? Because it's concave down. This is what we talked about last time. When you have a concave down graph, it's because your average rate of change is decreasing and vice versa. What about from 1 to 2? Increasing, and again, why? Concave up. So we're going to continue to layer these things with average rates of change as we learn different functions. In this class, every time we learn about a new function, we will talk about its average rate of change and how it's related. Sound good? Okay, time for some calculator work. So on the AP test, there are sections with and without your calculator. A question like example 4 would be on a calculator section because it's nearly impossible without one unless you're crazy good at graphing decimals in 5th degree functions, which I don't think any of us are. But this is actually a very easy problem when you have your calculator. So everybody right now, I want you to open your calculator, clear it, because who knows what was in it beforehand. And I want you to go type in that function into y equals. So we have this question that says for 0 to 3 seconds, the number of cars in a parking lot at time t hours can be modeled by this function cars c of t. Based on the model, at what time t does the number of cars in the parking lot change from increasing to decreasing? We'll talk about what that means in a second after you type it in. Now, if we press graph today, I messed up. What did I mess up on? Wow, that's embarrassing. Okay, fixed. Here's what it looks like. And that's not really helpful to look at. And today, when we've been learning, we've been looking at all of the graphs. So let's make this more useful. Last class we talked about how to change the window. Or you discovered that on that little activity we did. What x values, or t values in this case, are we interested in based on the problem? From 0 to 3. This is our minimum x value. This is going to be our maximum x value that we even care about for this problem. So why don't we change our screen to only see the stuff we care about for this problem? In your calculator, you go to Window, which is up at the top. Let's change our x minimum to 0 and our x maximum to 3, because that's literally all we care about. And press Graph again. Now what's happening here? I'm helping you problem solve. It like goes off screen, right? So we want to see up higher. How do we do that? Change the y maximum. Now at this point, you're just playing a guessing game. And to speed it up, let's put in 50. If we change it to where the highest we see is 50, we now see a screen that looks like this. Okay? On your paper, let's graph what that looks like, so when you look back at your notes later, you're not like, where did all this stuff come from? So we had this is 0, this is 3, and this is 50, just so it kind of looks like your calculator screen. And we had a graph that does this number. Something like that. The question here says, based on this model, which we now see in our graph, at what time, t, which is these numbers, does the number of cars in the parking lot change from increasing to decreasing? If we are going from increasing to decreasing, what kind of extrema am I looking for? A maximum. Awesome. So we are just trying to figure out what this maximum value, local maximum is. Here's how we do this, because you could just like move your little cursor along here, but you're never going to be accurate. Do y'all know how to find a maximum in the calculator itself? I don't think this has ever been shown to you before, so you can see. You're on the right track. So we're going to go to calculate on the graph menu, which is a blue word above trace. So we press second and then trace. Look at what word is on this screen. Oh my gosh, click 4. The calculator then walks you through instructions. It says left bound. What you're going to do is you're going to take this little, I call it a turtle because I don't know what else to call it. It looks like a turtle to me. You're going to take the little turtle and you're going to make sure the turtle is on the left of the maximum. Currently, is it on the left of the maximum? Okay, press enter. The instructions change. What does it say now? Right. You need to get the little turtle on the right side of the hill, on the right side of the maximum. So we're going to press right like a bajillion times until the turtle moves along your graph and goes over the hill. Make sure it actually okay, it's still more. It's significantly, it is across the hill, right? I can see that it's across the hill. I press enter. The instructions are going to change. What does it say? Yes. We don't do that. We skip that. So we press enter one more time. And it's going to identify the maximum for you. So on your paper now, you can write down that coordinate, that the maximum occurs at 2.446, 31.898. Okay. We just have to make sure we know how to answer the question. What time does this change from increasing to decreasing? Which one of those is representing time? 2.446 hours. The reason I know that is because time is along my x-axis, so the x-coordinate is actually a t-coordinate. This would be t and c of t, since we're using time and cars per time. Okay, pause. I want you to reset your calculator, and I want you to do this whole problem again. How do we reset? Second plus 712. That way you're double checking for yourself. You know how to do the exact problem we just did without my promptings.